Hello, everybody. My name is Sechito Isaac, and I'm with my colleagues Daniel Oyoka and Senkungu Martin Reino. We are from Group 5D, and we are presenting to you explainable machine vision techniques for cattle disease detection with deep transfer learning. First of all, we shall take you through the contents. Cattle farming is a cornerstone of global agriculture, and it's playing a pivotal role in food security and economic stability. And in many regions, you see that cattle provide essential products such as milk, meat, leather, and other byproducts critical to human sustenance. However, the industry faces a major threat from diseases such as foot and mouth disease. In our study, we look at machine learning methods of cattle disease detection, and we compare them to traditional methods of cattle disease detection, where these methods largely rely on manual inspection by veterinary experts. And while effective in controlled settings, these methods have several limitations, particularly in cases where many farmers, especially in rural areas, cannot afford access to veterinary expertise promptly. So in the last decade, technological innovations have revolutionized where cattle disease detection is done using artificial intelligence, machine learning, and deep learning techniques. In addition, there are also IoT sensors that aid in this process. However, there is still need for advanced user-friendly models to integrate high accuracy with interpretability, requiring stakeholders to make informed decisions and improve cattle health and enhance on the productivity through XAI techniques. Cattle diseases such as foot and mouth detection pose a significant threat to agriculture, impacting productivity, economic stability, and public health. Thus, we find that current diagnostic methods are based on manual veterinary inspections, which are time-consuming, costly, and inaccessible, most especially in rural areas. And our aim is to have these technologies accessible in rural areas, and we need them to a certain extent cheap and affordable to them. In our research, we aim to develop an interpretable and accurate deep learning-based system for detection of cattle diseases, specifically foot and mouth disease, by leveraging XAI techniques to provide actionable insights and improve trust and adoption among veterinarians and farmers. The specific objectives, we need to collect high quality cattle image datasets, and we're going to look at the dataset that we acquired, showcasing symptoms, foot and mouth disease, and pre-processing. And the other objective is to develop and fine-tune 7 deep learning models for cattle disease detection by leveraging deep transfer learning for pre-trained architectures. So the scope of this study was focused on the development and evaluation of deep learning models for the prediction of cattle diseases, specifically foot and mouth disease. And then the research included the collection and pre-processing of cattle image datasets, the development of deep learning models like CNN tested 1-to-1, the Vision Transformer, the PGG19, and also the integration of explainable AI techniques such as LIME, GradCam, integrated gradients, and occlusion to interpret the model's predictions and enhance transparency. We talk about the research contributions. We have developed 7 deep learning models to improve machine vision accuracy towards cattle disease detection, foot and mouth disease, and then we have also applied deep transfer learning to our models to improve their performance. We have applied explainable AI techniques such as LIME, gradient class activation map, integrated gradient, and occlusion to our models. Then we also developed a Django web-based application with a friendly user interface for farmers to upload cattle images, detect presence of foot and mouth disease, and help them in monitoring their cattle health. Significance of the study to technology, we have advanced AI interpretability in agriculture, to society. It promotes livestock health and food security through early disease detection. Farmers provides affordable, accessible, and efficient cattle disease diagnosis. We move into the implementation phase. Uh, the dataset that we acquired, it comes from RoboFlow Universe. This is the world's largest collection of open source computer vision datasets and APIs. It contains almost all images that you may want to, or images of or datasets that you may want to acquire. So we acquired these datasets and we performed augmentation of them. So these images that we acquired 170, the dataset that we acquired contained 173 images of healthy cattle. 51 of them were affected foot and 313 of affected mouth. And after we performed augmentation to overcome these class imbalances. So on the dataset that we acquired, we performed image augmentation, and these are the techniques that we used. We used rotation, flip horizontal, brightness, contrast, blur, and noise. And then also we have the classes affected foot, affected mouth, and healthy cattle. So we split them into the train set, the validation set, and then the test set. When we do the image pre-processing, you can see that the data augmentation that we did gave us 350 images from affected foot, 350 from affected mouth, and then also we split them into validation where we have 75 images. You can see that a complete data set has total number of 350 images for the healthy cattle class, affected foot, and affected mouth. So the total balanced dataset has a total 1,350 images, whereby 70% is in the train set, the validation set has 15%, and the test set has 15%. And you can see the summary of the class distribution. We move on to have insights. We needed to generate insights from the through use of an exploratory data analysis. And you can see we have the overall class distribution analysis. So you can see the train set. It is averagely distributed, the validation set, and then the test set. And also we have this pie chart to demonstrate the class distribution. And then also the dataset split distribution here, and also the stacked distribution by split. So by all means, we have very many insights. And then also the image dimension distribution. You can see that when we pre-process these images, we say that, okay, let every image have almost 224. We say 224 images for each pixel, so that the image input into these models is of a standard, so that the models give us what we want. And then also the aspect ratio distribution, and we have this box plot for the file size distribution by class: healthy cattle, affected foot, and affected mouth. Then we proceed and we bring up sample images for each class. And also we have the RGB distribution for each class. So we have the image normalization process shown here, where we did some normalization where we have the original image, and you can see this is the pixel distribution. This pixel distribution is before normalization, where we have the mean and standard deviation represented there, and the pixel values and their densities represented accordingly. And you can see the image after normalization. You can see the normalized pixel value, and then also the density, the mean and standard deviation. So we did that for almost every class: the healthy cattle, affected foot, an infected mouth.
Hello everyone, my name is Daniel Ayoka and I'll be presenting to you the methodology, the deep transfer learning phase and the assembly learning phase of our project entitled Explainable Machine Vision Techniques for Cattle Disease Detection, whereby we are focusing mainly on foot and mouth rot of the cattle disease. Well, as you can see in our methodology, we had about 5 phases, and in the first phase, that's the data collection and class definition. Well, we gathered our data sets from various sources that includes RoboFlow and Zenedo and data.org and tried to define our partial classes of interest, and that was the healthy cattle, including images of healthy cattle foot and healthy cattle mouth, and then also in the other classes we had an infected mouth class and an infected foot class, and after that phase we had to pre-process our data to help us train our models perfectly, and in the pre-processing phase we carried out a number of processes, and among them we had to standardize our images into a format and to so as to have a zero mean and then have a unit variance across all our images. And then for the data cleaning, we had to eliminate images we're not interested in, and then also in the normalization, we had to scale up our images over as a particular value that's between 0 and 1 to enable our models to converge and train perfectly. Then in the data augmentation, since some of our classes were not we not had different varying number of images, and there was a great class imbalance. You had to carry out data augmentation to help us provide a diverse number of images to train our models properly, and also to help our models generalize and also reduce overfitting of the models. Then finally, we had to carry out data splitting. In that phase, we had to define a particular number of images that we're going to use to train our models, then others to validate it, and also to help us test the model performance during training. So we split our data into 70% for training, then 15% for validation, and 15% for testing. And then we headed into our third phase, phase 3, and that's the training phase, whereby we had to carry out training our models. We first of all had to define our models of interest, whereby we defined 7 models. Among them, we had the ResNet 50, the DenseNet 121, and the VGG 19, and the MobileNet, and the ConvexNet, and the VITNet. Then we in the first phase of our training, we trained our models on basic configurations, and we realized that our models performed poorly, as we shall discuss later on during the presentation. Then what we decided to do is to apply deep transfer learning to help us improve the model's performance, as you can see here. So for deep transfer learning, well, we carried it in two phases as well. First of all, we had to first do feature extraction. This is whereby we had to freeze all the layers of these modules and then only leave the classification layer, then train the modules to help the classification layer adapt, gain weights, adapt to our dataset. Then in the second, we did the fine tuning by unfreezing all those frozen layers and enable all layers of the models to train and acquire weights and understand our data set. We realized after that our performance, the accuracy increased greatly after that process of fine tuning. Then we realized that after that we had to go into our fourth phase, and in this phase we carried out ensemble learning. Reason for that, after carrying out deep transfer learning, we realized that some models, well, they were performing better in a particular class, and others were good in a particular class, and other models were confused. So we tried to wanted to enhance our predictions and performance of our models. So we had to evaluate those models and understand and get a good prediction. That's why we carried out ensemble learning. And the techniques we used for ensemble learning, we used the average weight, the average weighting, and then we also use the majority voting and the performance weight voting to get the best performing models. And then among those models we had the ResNet 50 and the DenseNet 121, and then the EfficientNet, and finally we evaluated those models, as you can see here, on various performance metrics, the recall, the precision, accuracy, and F1, and then also the rock curves to help us to understand how the model performs across different thresholds including the lowest threshold, the medium, the average, and the highest threshold. Then also the confusion matrix to understand which particular classes confuse our models. Then and lastly, in this phase, we are trying to also carry explainability to the predictions of our ensemble model, just to know which particular features are of the images provided to the model that it bases on to tell us that a foot is either infected or a mouth is infected, or either it's the foot or a mouth belongs to an healthy class. Then finally, in the last phase, we wanted to deploy our mod. We deployed our model, to a cloud to enable our end users, those are the farmers, local farmers, and the veterinary doctors, to access our system to help them make timely predictions on by uploading their images. And in this phase, we had to first of all convert our model into a format that we can easily deploy in a Django system, and also optimize its performance so that it's around 2.5 times better than the PyTorch model. And then in this case, I would want to walk you through some of the performance of our models. So here we try to evaluate the performance of our models, and in this case, for this case here, the baseline models, we showed you, we visualized how these models performed in terms of precision, recall accuracy, and F1 score, and also the ROC curve, then the training time, and these values all belong to the baseline models, the models we trained before the deep transfer learning. Then after here, we showed you that we visualized the improved model performance, and here it shows that according to accuracy here, you could see that the accuracy of the improved models is greatly higher than that of the baseline models, indicating that our models are improved greatly after deep transfer learning. Then there we try to show you how these models performed in terms of the improvements, and then also try to visualize the performance across a particular metric for both the two phases. Then here we went ahead down and tried to implement ensemble learning. Let me walk you down straight to the part where we did it. Yeah, here. And in this case, we try to show you how the ensemble things. We defined the methods, the weighted average, the average weighting method, then also the majority voting, then also so that we came up with those three models. And here it shows you how the performance of each of the ensemble model across different classes in our data set. And also here we try to inference and show you how the model performs on our test set. And in this case, let me walk you down here, and you can see here we have to try to apply also explainability, and this is for this is for an infected foot, how the model tried to give us results for an infected foot. As you can see here, it predicted it as an infected foot with a confidence of over 99%, and the method is performance weight exact method. And then also try to show you the grad cam attention hit, then there's also the segment importance of the line explainability, then the pixel attribution from the generated gradient, and the occlusion sensitivity, the region importance. Yeah, basically that's what we did in our project. For that case, I will allow my fellow colleagues to continue with you.
For explainability, we applied integrated gradients where we have the original image that comes as a whole full image, and then it generates a baseline input image, which is a black image that has zero input, and then it interpolates between the baseline image, which is this image, and the actual input. So once it interpolates, it comes up with such an image that is a gradient of the output with respect to its input along this path. So the integrated gradient integrates these gradients over the path to get feature attributions in which the model is basing on. The second explainability technique that we applied is GradCam, where we visualize which part of the image, and you can see that it visualized this mouth. So the part of the image feature on which the ResNet 50 was basing on was this mouth. So it computes the weighted average of these feature maps using the gradients, and then produces a heat map. So you can see that it is computing these weighted averages and producing a heat map. So it shows the heat map of this mouth, showing that it's based on this mouth to predict infected mouth. So this heat map highlights important regions in the image that influenced the prediction. Then we also applied occlusion to the model, So we have occlusion applied here. The way occlusion works, it takes in the input image and it systematically blocks it or occludes the image into small patches of the images, i.e., it can use gray squares or even blue or black squares. So it passes each occluded version through the model and records the change in the prediction. So after recording the changes in the prediction, it generates a heat map showing the regions. And you can see here it is still showing the mouth. It's based on the mouth to predict mouth disease or infected mouth disease. So these regions, when blocked, it reduces the confidence, meaning that these regions were important. So we repeated the same explainability techniques over all models and over all classes. For infected foot, you can see that we applied integrated patterns on the on the infected foot. Also, we applied QuadCam on the infected foot, and you can see the heat maps that have been generated by occlusion, by Lime, by QuadCam, and we did the same thing for the vision transform. So still on the ResNet 50, we also did it on their hooves, on the foot to find out the foot and mouth. So you can see that it is generating heat maps here for the healthy feet. So basically, that was it. I would like to invite my next colleague to take you through the next part of the session.
It's good afternoon. Sam Congrano Martin, and I'm going to be taking you through the remaining parts of the slides. These are some of the confusion matrices of the models that we trained. The first one is a confusion matrix of DisNet 1 to 1. The second one is a confusion matrix of the VIT, that's the vision transformer. And then the last one is a confusion matrix of the ResNet 50. After training our models, we went ahead and made some sample predictions. Here we used the ResNet 50 model to predict and see whether the models are working very well. Uh, we provided the model with an image of a healthy cattle, and it predicted that indeed it was a healthy cattle with a confidence of 0.998. And then after I uploaded an image of the uninfected foot, and the model predicted that it is indeed an uninfected foot with a confidence of 0.979. After developing our models and training them, we added explainability in order to make sure that the users get insight of what the model is based on while making their predictions. These techniques, we integrated the Lime, GradCam, integrated gradient, and oscillation. After training the models, we added explainability to see what exactly the model is based on when making their predictions. Uh, these are some of the samples. First, we have the infected foot, and after applying GradCam in the above image, there we see the red spots and the yellow spots shows the pixels of the image that made to the or contributed most to the prediction that indeed it's an infected foot. And here we have the infected mouth. The images, the explainability images show that brighter spots that contributed most to the model's prediction, and then the dark parts, those are the ones in blue, they contributed negatively to the model's prediction. Uh, uh, Furthermore, we have further samples. Here we have the the infected foot and the infected mouth, uh, and we show also the explainability for the integrated gradient in the second column, and then the third column have the GradCam, and finally the occlusion with the sharp images that show in red and yellow color, those are the brighter colors that show the contribution to the model's prediction, and then the dull color of the blue, those are the parts of the image that contributed negatively to the model's prediction. Then system development, we developed a Django system using the Django framework, and the system we used the PostgreSQL database for storing the data about the system. The system uses the inbuilt Django authentication to authenticate users. The cattle to be diagnosed are registered on the system. This helps in the monitoring and the tracking of the health of the cattle. The image of the registered cattle is then uploaded to the system, and the model determines whether the cattle is healthy or is infected by foot and mouth disease. The diagnosis history is kept in order to keep track and monitoring of the health of the cattle. Um, then the system produces the XAI images to help provide insight to the users so that they may know what the model is based on to predict or to give their predictions. Welcome, I'm Rhino Martin. I'm going to take you through the system. This is our system. This is a login page where people put in their credentials to access the system. I already have an account here, so let me just log in. Now the system goes direct to our dashboard, and this is the dashboard. You can see we already have registered 17 cattle, and after diagonizing we saw that one is healthy and the rest are infected. The pie chart shows the infected in red and then the healthy in green, and then the infected types. You have the foot infection and then the mouth infection on this bar graph. Then here on the line graph, we have the infected foot, infected mouth, and the healthy cattle, showing their trend over time. uh, we have the upload page. This is where we diagnose the animals from. After registering the animal, we come here and select the animal that we registered. Let's take this, and then we choose an image. Let's say we've selected this one. Then we upload the image, and then we test to see whether the cattle is healthy. Or as you can see here, the model has detected that indeed this is a foot infection and the cattle is infected. We have the history page where all the diagnosed animal, the history shows the information about the diagnosis. You can see the animals, and the test results are also kept. Then you have the registration page where we can add an animal or register an animal. We add the tag number, the age and the breed, and then we register that animal. After registering, you can see that the total number of cattle has increased from 17 to 18. Now the user can actually log out and maybe can sign in another user. Thank you so much for listening and watching.